All right. Good afternoon. Today we are gonna start covering cylinders, a new mechanical component that we look at. Before we start, any questions? All right. We are gonna talk about the cylinders. The examples for the cylinders can be pressure vessels, which they contain gas or fluid, or it can be a pipe carrying high pressure fluids. So that high pressure fluid is gonna develop stress inside the pipe. Also, it can be a hydraulic cylinders, another example for that. So these are some examples for cylinders. I mean, it can be something like this with the inner circle and the outer circle, and it's the thickness of cylinder. So we are covering three types of the cylinder problem. One, pressurized suppose pressure vessels, the examples for that, or a pipe carrying the high pressure fluids. So just it can be under internal pressure. Just think about some pressure applied inside this circle, and or external pressure if you apply external pressure on an outer surface. So if this is the cross section of this cylinder with the length of L, it can be under internal pressure, PI, and or external pressure. We might have inner and outer pressure at the same time, or just one of them short. So we would like to know, if we have pressurized cylinder, what kind of stress is going to develop in the cylinder. So we look at those terms. And for pressurized cylinder, we are going to look at two different cylinders. Thin cylinder and thick cylinder. The stress would be different in these two types of the cylinders. We call thin cylinder if the thickness, which is this, versus over the inner radius, which is this guy, is less than or equals to 0.1. So, and if it's greater than 0.1, it's considered as a thick cylinder. So stress analysis for pressurized cylinder would be different in these two types of the cylinder. The second type of the problem that we are covering is rotating cylinders. Consider the flywheel or blowers, which they rotating. Due to the inertial forces, we are going to have some stress developed in, through the cylinders. So flywheels, blowers, or even a disc which is rotating at a high speed. Due to the inertial forces, we are going to see some pressure, some stress developed in the cylinders. It's assist cylinders. And the third part of the problem, if we have two cylinders, one smaller, the other one is larger, just the outer diameter of this cylinder is slightly greater than the inner diameter of the larger components. How can you attach these two? One way can be if you just apply press fitting. By press fitting, just compress this and insert into the second component. So due to the press fitting, we are going to have some stress developed in the component. So we are going to look at this type of the problem as well. So now, I will start with this one, thin cylinders, but before we start that topic, let me talk about Cartesian coordinates versus cylindrical coordinates. So if this is a cross section for cylinder at any point, suppose this point, which has a distance of r from the center of the cylinder, if I want to draw the stress element, this is the x-axis, this is y-axis, for example, and z-axis coming out of the plane. So if I want to draw the stress element, it's going to look like this. Sigma x applied here, sigma y applied there. So we have this state of stress. And we have Cartesian coordinates because we have x and y. But we can have different coordinates, like cylindrical. For the same point, instead of having this state of stress, I'm going to have stress elements in this form. Sigma x and sigma y, they are going to change to sigma r or radial and tangential, sigma t or theta. So sigma r, radial, stress, sigma t or theta, tangential. So for cylinders, we are dealing with sigma r and sigma theta rather than sigma x and y that we used to have in our analysis, because we just changed the coordinates from the Cartesian to the cylindrical. Here, the stress applied to this direction is called sigma z. If we have planar stress, it's going to be 0, but if it shows up, we are going to have sigma z. Here also, we are going to have sigma z, which applied along the cylinder. Sigma z is going to apply along the cylinder. We call sigma z line. So radial stress, tangential, and longitudinal stress, which apply along the cylinder. So So now I'm gonna start talking about a radial stress in cylinder in the thin cylinders. Thin cylinders means the thickness divided by the inner radius is less than or equal to 0.1. So we can prove that in thin cylinder, sigma r is always equals to 0. So if we have something like this, which is a thin cylinder, at any point, sigma r, it's going to be equals to 0. We have sigma theta or sigma t, which is a tangential or perpendicular to the radius. So now, if this cylinder is under internal pressure, just imagine a pipe carrying a high pressure fluid. So you will see the internal pressure applied to the pipe. If I draw the cross section, you will see pi. So if I cut this pipe at any plane, it can be this plane or any other plane. So I cut this at this plane. So and I look at this size, pi. So due to this pressure, this internal pressure, we are gonna have, this pressure is gonna separate these two parts, these two halves. It's gonna separate them, but this pressure is gonna make some stresses on the on this thickness that we call sigma t or sigma theta, because it's perpendicular to this line. So sigma t or sigma theta is going to develop in these two thickness. We are going to find this value. So this pressure is applied along the cylinder. So this pressure times the area is going to give me the force that this internal pressure is going to make. So the internal surface, the effective surface is going to be di, which is this, times the length. So area would be di times L. So this pressure is applied to this area. So if I want to find the force coming through this internal pressure, is going to be pressure, internal pressure times the area. So the force would be Pi times Di times F. So this force is supported by these two stresses. So sigma T times this area. The area is, the thickness is T times L. I have two of them, 2 times T times L. So sigma T times 2T times L is going to be the force coming from the internal stress. So if you equate these two forces, because they should be the same, I can cancel out this to L. Sigma tangential would be pi times di divided by 2 times t.
Dr. Gaudy, is that the di, is that internal diameter?
Yes.
Why use that instead of internal circumference?
We assume that there's gonna be, the effective. I know what you are saying. You're saying that this area is gonna be the effective, should be considered as an effective area, but basically, if I have this, which is the half parts of the cylinder, and the internal pressure is applied here. If we measure the force, we will see that the effective area is going to be this line times this length. Although I can see what you are saying, because you are saying is applied to this parts of, or this length of the cylinder multiplied by L, but the force is gonna be, we are gonna find the effective length, which is not this one, it's gonna be the diameter.
Okay.
So if I want to start from scratch, I use this one because it makes more sense, but the explanation that I can have is the effective, if we use the effective length, it should be the diameter, not the this length. The di is 2 times r, 2 times r divided by 2 times t. It's going to be pi times r divided by t.
Should we specify that as RI or just R?
Pardon?
Should we RI or just R?
I mean, since it's a thin valve, RI, RO would be the same, basically. RI equals to RO. So we only have tangential stress when we have a thin wall cylinder, sigma r equals to 0. Now, think about pressure vessel where we have a cap at the end. So the cap is going to be applied at the end of cylinder to close the cylinder. So that pressure is going to apply to the cap. Find me the force applied to the cap due to the internal pressure. So find me the force applied to the cap if I close it. And it's going to be in z direction, because z direction it goes up. Then I will talk about this stress, longitudinal stress, sigma z or sigma n. Is that clear what I'm asking? FZ. I mean, suppose I put at the top. Although it doesn't matter if you put at the bottom, this goes the other way. Anyway, it's gonna apply force to the cap.
R squared.
Okay, say it again.
R squared times the area.
The area is
It's the bottom cylinder circle, so R squared
okay.
times
Times
internal pressure.
internal pressure. Exactly. I mean, this is the force. Thank you. This is the force coming through the internal pressure applied to the cap. So this force is supported by this area. So the area is gonna support this force. So it's making a stress in z direction. So sigma z times the area, which is this side, it's gonna be 2 pi times Ri times the thickness. If you just expand this, you are gonna get something like this, 2 pi Ri times thickness. So it's gonna be sigma z times 2 pi Ri. This force should be equals to pi Ri squared pi. I can cancel out one of the Ri, 2 pi, one, the pi's can be cancelled out. Sigma z is gonna be pi Ri divided by 2 times, I forgot t. 2 pi Ri times t divided by 2t. So in a thin valve cylinder, if there is no cap, the only stress is gonna show up is tangential, which is pi r divided by t. What is the direction? At any point, just tangential. It's a tangential, and in radial it's gonna be 0. If we have cap, then we are gonna have sigma z coming out of the plane. So in any case, these two would be the maximum number of stress that you would see. Good. So now, for any point in the cylinder, if you draw the stress element, these are two normal stress applied to that. Now, find me the principal normal stresses and tau max. sigma 1, sigma 2, sigma 3. What are those three variables, and what would be the maximum principal normal stresses? What would be maximum shear stresses? Number 15. What should be the principal? What do you think? I mean, what do you think about principal normal stresses? What should be the sigma 1, sigma 2, and sigma 3? Just look at this. We don't see any shear stress. Means these are the principal normal stresses. We just need to order them. So sigma R is 0, 1, 2, 3, and no shear stress showing up. So the greatest is going to be this because P is always positive, R is positive, thickness is positive. So we have tensile stress for the tangential, and it's greater than this. So sigma 1 is the greatest, which is sigma T. The second one still is positive, but it's smaller than this, so sigma Z. And sigma R is 0. And after you rank them, the maximum shear stress is always sigma 1 minus sigma 3 divided by 2. So maximum shear stress would be Pi R I C minus 0 divided by 2, Pi R I divided by 2T. And as you see, for any point, it doesn't matter what would be the R, because it's a thin valve, so we assume that the radius for all points on the valve is going to be the same, so we don't have different value of the stress for the different points. So any point in this thickness, in the cross section, they are going to see the same sigma theta and sigma z, if there is a cap. All right, let me work on one example. I will rewrite sigma z, sigma t. Right here. When we cover the failure theories, we will go to talk about the different theories which exist to help us estimate the failure on a mechanical component. But to work on this example, I just introduced two theories briefly, but we discuss in detail when we go to the failure theories. So the two theories that I'm going to talk about, that is, one is maximum shear stress theory, or MSST. Again, these theories are going to help us to estimate the failure on a mechanical component. They are going to answer this question: are we going to have the safe design, or we are going to have failure? So to have, based on this theory, to have a safe design, the maximum shear stress applied to the component should be less than or equals to SSY. What is this SSY? SSY, it depends on the material that you have used for the component. So shear yield strength, which is equals to SY divided by 2. And SY is a yield strength. It's coming from the table, depending on the properties of the material. If you divide it by half, you can find this side. As long as the tau max is less than SSY, we have a safe design. And factor of safety is defined as SSY divided by tau max. So whatever is the maximum allowable, whatever is the shear yield strength divided by the maximum shear stress applied to the component. If you recall, tau max is always sigma 1 minus sigma 3 divided by 2, and just replace this. And SSY is SY divided by 2. So I can cancel out these two, SY divided by sigma 1 minus sigma 3. This is the first theory. The second theory, we call it distortion energy theory. DET. The distortion energy theory says if you want to have a safe design, one misses stress. I will define one misses. Should be less than or equals to SY. As long as the one misses stress is less than or equals to SY, we are going to have a safe design. And N factor of safety is defined as SY divided by sigma 1 misses. 1 misses stress. I defined 1 misses stress right here. 1 misses stress for plane stress, where we have sigma 1 and sigma 2. Sigma 3 is not going to show up. It's going to be sigma 1 square plus sigma 2 square minus sigma 1, sigma 2 square root. For plane stress. There is a general form of a question for one misses if we have three-dimensional. We will talk about that on failure theories later, but for now, to work on this example, that's enough if we know one misses stress can be calculated by this equation. If you have plane stress, you have two principal normal stress showing up, sigma 1 and sigma 2. And this equation is going to give us one value, and we compare it with Sy, and we can say if the design is safe or we are going to have failure. And factor of safety can be defined by this. It's obvious that if the factor of safety is less than 1, means tau max is greater than SS5, so we have failure. So if you want to have safe design, NF should be greater than 1. If you want to be more conservative, you should get the higher value for, greater value for NF. So let me question about this two. Yes.
The safety factor for DET is SX or SY?
And this is SY, yield strength. And it's coming from the properties of the material. Yes.
Could you just tell me what word came after sigma zero? I can't.
This one?
No, sorry, the word that you used to explain what it was. Yeah.
One missile. I mean, it's a. The point is, we have principal normal stresses, sigma 1, sigma 2, sigma 3. But we only need one value to compare with the SY. So this theory is going to help us to define one value which is coming by this equation, and then compare sigma, that value which is a one missile stress, with SY. So this is just, we define that. It's coming, it's a mathematical equation, basically. Because here we have sigma 1, sigma 2. Which one should be compared with SY? So this theory says, if you, based on the distortion energy theory, you can find this value and compare it with SY. All right. For a thin valve cylinder, so we have a thin valve cylinder. SY, the yield strength, the cylinder is made of the material with the SY equals to 60 kpsi. This cylinder is under internal pressure of 300 psi. Suppose we have a pipe which is under internal pressure of 300 psi. It's made of a material with this yield strength. Consider factor of safety equals to 3. Design or find the valve thickness. What should be the C? We are doing the design. So we are gonna use maximum shear stress theory and distortion energy theory. We want to design with applying these two theories. One for this one, then we try with this one to see what is the difference between these. Let's start with maximum shear stress theory. Factor of safety is defined by Sy divided by sigma 1 minus sigma 3. This is how we define the NF. NF is 3. 3 equals to SY, which is 60,000 PSI, divided by sigma 1 minus sigma 3. So then it tells me sigma 1 minus sigma 3 should be equals to 20,000. 60 divided by 3, this should be 20,000. What was sigma 1? Sigma 1 was this one, sigma 2 was this one, and sigma 3 was 0. So sigma 1 was pi times Ri divided by T. I forgot to say about the diameter. Diameter is 100 inch. The inner diameter is 100 inch. So sigma 1 is going to be pi, which is 300 psi, times the radius is half of the diameter, divided by t. I'm looking for t, so I leave it there. Sigma 3 is 0. Sigma 3 is 0. Just plug in the values right here. 300 times 50 divided by t minus 0 equals to 20,000. So the t would be 15,000 divided by 20,000, which is 0.75 inch. So as long as the thickness is greater than or equals to 0.75 inch, the cylinder is not going to fade under that factor of safety. If you change the factor of safety, it's obvious that everything is going to change. But this is for MSST. Question on this. All right, let's look at apply the other theorem, distortion energy theorem. Distortion energy theorem, it says NF, or factor of safety, is SY divided by 1 meter. I should find 1 meter stress, which is sigma T square plus sigma Z or L square minus sigma T times sigma Z square root. Sigma T is sigma 1. It's 15,000 divided by T square plus sigma Z is half of this, so 7,500 divided by T square minus multiplication of these two, 15,000 times 7,500 divided by T square square root. I'm just calculating the 1 misses. Sigma 1, sigma 2, 1 times 2. Sigma 1, sigma 2, 1 times 2. If you add them up, you will find sigma 1 misses equals to 1299, 0.38 divided by T. 12990.38 divided by t. This squared divided by t squared. This squared divided by t squared minus this divided by t squared, the summation square root. Everybody can see why we got, how we got this. All right, now back to the definition of factor of safety. Factor of safety is SY, which is 60,000 divided by 1 meter, 12990.38 divided by T equals to what would be the factor of safety, which we are supposed to use 3. So then solve for this T. 3 times this equals to this, and the thickness would be 0.6495 inch. The thickness for distortion energy term. All right, let's look at the toolbox that you are supposed to use, N representing thin cylinder on the line 2. So N, capital N, capital C. The rest, I mean, it's gonna, if you type, it's gonna bring this. On very top line, you can see English units. So here we don't have SI, we have English units. So I check mark this. The inner pressure was 300. And inner radius diameter is 100. The inner is 15. Wall thickness. I'm solving for wall thickness, so I leave it there. I don't know what would be the value for that. So I just enter this safety factor that I'm given, which is 3. And for the material, it has a library that you can choose the corresponding material. And the last line is the user specified. Since we don't know which material we have, I click user specified, and it's asking for SY, yield strength. 60,000, 60E3, 60,000, or you can enter 60,000, 6 and 4 zeros. And then, if I click calculate, it's gonna say your wall thickness. Wall thickness for maximum shear stress theory should be 0.75. For distortion energy theory should be 0.6495 that I got there. And the safety factor would be the same for both. So if you are given with the wall thickness, you leave this 0, it's going to calculate the safety factor for you. If you compare these two, 75 versus this method is more conservative than the other one. Because this thickness is valid for this distortion energy theory, but we are going to failure on